Good morning, everyone. Welcome to the course Introduction to Structural Stability, Concepts and Applications. Let's continue the discussion on structural stability. In this class, we will have another example on spring bar models. Unlike the previous one, where there was a moment that was acting in addition to axial force, in this problem, we will have a lateral force Q that is acting. So, for the spring system shown here, using large deflection theory, derive the equation defining equilibrium condition and the equation defining the limit state of stability, assuming the rod to be rigid. Express the equations in terms of the non-dimensional parameters P by Ka and Q by Ka and rotation theta of the rod. Draw plots of P by Ka versus theta and repeat the above using small deflection theory. So this is the problem that we have on the right hand side. There's a sketch is shown. So for the loaded condition in this system, there are three possible deflections shown as theta, small delta and capital delta. So as you can see from the right side, when all the three loads are applied, which is the axial force P, and then there is a restoring force F, and then there is a destabilizing force Q that is acting, due to which the spring bar model will rotate by an angle of theta, and then due to which there will be a lateral displacement small delta and an axial displacement capital delta. The distance of A, which was the length of the rod prior to the application of load, now reduces to A cos theta. So recall the three necessary and sufficient conditions. The first one is the equilibrium equation sigma MA equal to P delta plus QA cos theta minus FA cos theta equal to 0. Here we are considering counterclockwise as positive, so we are taking the moment about at the point A. Then there is a stress strain relationship F equal to K delta and the strain displacement relationship delta equal to A sin theta. Eliminating delta and F from the above equations leads to PA sin theta plus QA cos theta minus KA square cos theta sin theta equal to 0. This becomes equation 1a. Now we are simplifying this equation further by dividing by A sin theta throughout the equation. So this becomes P plus Q into cos theta by sin theta minus Ka cos theta equal to 0. Further simplification, we get P by Ka equal to cos theta minus Q by Ka divided by tan theta. This becomes equation 1b. Equation 1a and 1b defines the equilibrium position by relating P and theta for given Q, K and A. Here Q is the lateral force that is acting, K is the spring stiffness and A is the length of the rod. Now for loaded condition, again we have to consider the limit state of stability. In order to achieve the limit state of stability, we have to use the perturbation technique. Perturbation technique is an additional load that is applied to the structure when it is in a loaded conditions by displacing it further slightly away from its stable position, which is theta star. So consider the perturbed position theta plus theta star, for which 1, 2 and 3 take the form. So the 4 is the equilibrium equation sigma MA equal to P delta dash plus QA cos theta plus theta star minus F dash A into cos theta plus theta star equal to 0. So as you can see from the picture on the right side, you can see that in the equilibrium position, due to the perturbation of the loads, the displacement of the rod moves from theta to theta plus theta star, and the lateral displacement actually moves to delta dash. So the strain displacement relationship delta dash equal to A into sine of theta plus theta star. So similarly, when we eliminate delta dash and F dash from equation 4, it leads to the following equation sigma MA equal to PA into sine of theta plus theta star plus QA into cos of theta plus theta star minus Ka square into sine theta plus theta star into cos theta plus theta star. So this equation can be simplified by the following assumptions. When theta star is very small, theta star may be made as small as desired but not 0. we have sin theta star equal to theta star, cos theta star is equal to 1. So we also know the trigonometric equations we have studied in your high school. Sin A plus B equal to sin A cos B plus cos A sin B, and cos A plus B equal to cos A cos B minus sin A sin B. Here instead of A and B, we have theta plus theta star. So sin theta plus theta star equal to sin theta cos theta star plus cos theta sin theta star. But we also know that small values sin theta star equal to theta star and cos theta star is equal to 1, which gives you the equation sin theta plus theta star cos theta. The next equation is cos theta plus theta star is equal to cos theta star minus sin theta star, which again gets simplifies to cos theta minus theta star sin theta. So when we multiply sin theta plus theta star into cos theta plus theta star, we get the following equation. Basically sin theta cos theta minus theta star into sin square theta plus theta star into cos square theta minus theta star square into sin theta cos theta, which again we can simplify this further by saying that sin theta cos theta plus we can take theta star common, which gives you in the brackets cos square theta minus sin square theta minus theta star square into sin theta cos theta. We also know that cos square theta minus sin square theta is equal to cos 2 theta, and we also know that when small values of theta, the theta star actually becomes very small, so that this part of this one can be neglected. Substituting for above trigonometric equations, we get sigma ma equal to PA into sin theta plus theta star plus QA into cos theta plus theta star minus KA square sin theta plus theta star into cos theta plus theta star. So for the above trigonometric identities, we further get this one. We have sigma ma equal to PA into, instead of sin theta plus theta star, we are substituting sin theta plus theta star into cos theta. Similarly, for cos theta plus theta star, we are substituting cos theta minus theta star sin theta. And for sin theta plus theta star into cos theta plus theta star, we get the equation sin theta cos theta plus theta star cos 2 theta. So when we substitute all that stuff, we get these following equations, which again can be simplified further by expanding it. So this becomes PA into sin theta plus PA into theta star cos theta plus QA cos theta minus QA theta star sin theta minus KA square sin theta cos theta minus KA square theta star into cos theta. By expanding this equation, we can separate out the terms that are corresponding to theta as well as theta star. So we segregate the terms that does not have theta star and segregate the terms that has theta star. So we rearrange the terms, which gives you PA sin theta plus QA cos theta minus KA square sin theta cos theta plus theta star into A, which we take it as common, gives you P into cos theta minus Q into sin theta minus KA cos 2 theta. So recall from previous equation 1a, we know that PA sin theta plus QA cos theta minus KA square cos theta sin theta is equal to 0. So substituting that in the above equation sigma ma, we get this, the first term which does not have the theta square terms, theta star terms, actually becomes 0. And so we get sigma ma equal to theta star into A bracket open P cos theta minus Q sin theta minus KA cos 2 theta. We can see that if this term is greater than 0, it is in stable equilibrium. If it is equal to 0, it is in neutral equilibrium. If the term is less than 0, then it is going to be in unstable equilibrium. We also know that P by Ka equal to cos theta minus Q by Ka tan theta is the equation of equilibrium path, which is equation 1b. Equation 2b, which is theta star into A bracket open P cos theta minus Q sin theta minus Ka cos 2 theta is equal to 0, which is equation of limit of stability. So we have two equations. The one on the left is the equation of equilibrium path. The one on the right is the equation of limit state of stability. So we can further simplify 1b as P equal to multiplying the entire term with Ka, P equal to Ka cos theta minus Q by tan theta, which gives you the value P tan theta equal to Ka into cos theta tan theta minus Q, which again gives you Q equal to Ka cos theta tan theta minus P tan theta. This value can be substituted in equation 2b, which contains the term Q. So substituting this for q, we further simplify that theta star into a equal to p cos theta minus sin theta into ka cos theta tan theta minus p tan theta minus ka cos 2 theta. So this again becomes, when we simplify this further, we can say that either the terms in this equation can be 0, or we can say that theta star into a equal to 0. But a is a definite value because which is the length of the rod, and theta star is the definite value that is required to introduce perturbation. So they cannot be 0. Hence the bracket, the equations in the bracket should be equal to 0, which indicates that p cos theta minus ka cos theta tan theta into sin theta plus p tan theta sin theta minus ka cos 2 theta is equal to 0. So we can simplify this further. We can say that p cos theta minus ka cos theta into sin theta by cos theta, which is actually the definition for tan theta, into sin theta plus p into sin theta by cos theta into sin theta minus ka cos 2 theta is equal to 0. We can cancel cos theta out here. So we get p cos theta minus ka sin square theta plus p sin theta by cos theta into sin theta minus ka into cos 2 theta can be expanded as cos square theta minus sin square theta. So when we expand this further, we get the following equation: p cos theta minus ka sin square theta plus p sin theta by cos theta into sin theta minus ka cos square theta plus ka sin square theta equal to 0. We can see that there is minus ka sin square theta, the second term, and the last term plus ka sin square theta, which again can be cancelled. So we have p cos theta plus p sin square theta by cos theta minus ka cos square theta is equal to 0. So this again can be further simplified as p cos theta plus p sin square theta divided by cos theta is equal to ka cos square theta, which is taken to the right side. Now we can do the LCM. So we get p into cos square theta plus sin square theta divided by cos theta equal to ka cos square theta. We know that sin square theta plus cos square theta is equal to 1, which gives you p by cos theta equal to ka cos square theta, which implies p by ka. When we take the ka to the left hand side, it comes to the denominator. P by ka equal to cos square theta. This p by ka equal to cos cube theta becomes the equation of limit state of stability. So we have two equations: equation of equilibrium path on the left side and a simplified equation of limit state of stability on the right sides. So when we plot the graph with respect to pa and p by ka and theta, we get the following equation or the curves. So when we plot p by ka equal to cos theta minus q by ka divided by tan theta, we get a series of curves which are called as equilibrium paths. And when we plot the equation 1c, which is p by ka equal to cos cube theta, we get a nice curve which connects all the limit state of stability, which is also called the equation of limit state of stability. So note that when q equal to 0 in the above equation, p by ka equal to cos theta leading to two equilibrium paths. So when we plot this one, we have this equilibrium paths, one which is when theta equal to 0, p by ka equal to 1, when theta equal to pi by 2, p by ka equal to 0, which is the two limit state of equilibrium, as you can see from the right hand side. This point at which it is p by ka equal to 1 is also known as bifurcation point, and this type of buckling is also known as bifurcation buckling. So when you have to compare this with small deflection theory, basically what we have done so far is a large deflection theory where we have theta star component, and when we have the small deflection theory, we know that when theta is small, theta sin theta is equal to theta and cos theta is equal to 1. So the equation of equilibrium path becomes p by ka equal to 1 minus q by ka divided by theta, and the equation of limit state of stability p by ka equal to 1. So when we plot the above, we get the following equations. So the plot gives you p by ka in the y-axis and theta in the x-axis gives you the following curves. So the following curves, the equation of limit state of stability p by ka equal to 1 is a horizontal line starting at p by ka equal to 1.0 and stays the same throughout. And the equation of equilibrium path varies with respect to the value of q by ka. So the q by ka is equal to 0. It actually is the same as the equation of limit state of stability. When q by k equal to 0.1, you can see the red color curve, and when it goes to 0.2, then you have a green color curve, and then you have a purple color curve for q by k equal to 0.3, so on and so forth. So you can see that the equation of equilibrium path has a series of number of curves depending upon the value of Q by Ka, whereas the limit state of stability is one single curve P by Ka equal to 1.0. With this one, we complete this second problem on the spring bar model. In the next class, we will be talking more about Euler column buckling. So thank you so much. We look forward to you meeting in the next class. Thank you.